Today, we want to look at another density-based methods, DenClue, and also we want to look at another grid-based method, click. Click is very interesting because it allows you, because the vast majority of the clustering algorithm will not work very well when you have very high dimensional data. And click allows you to explore clusters in subspaces. So we will start with DenClue. Earlier, we introduced a set of concept reachability distance, for example, on core points. And those were used by one group of density-based methods, dbScan, and other additional improvements to the algorithm. But DenClue, this density-based algorithm is based on the kernel density estimation method. So on this screen, I summarized the key ideas behind kernel density estimation. So the goal is when you have a sample of points, you want to know the probability density function of this random variable which generated this sample. How can we find out that? So the goal of kernel density estimation is to estimate the unknown probability density function of a random variable based on the sample points using a kernel function. We will talk more later, but a kernel function is a function that's symmetric, that has the property of the area under the curve is 1 because it's a probability distribution function. So here what I illustrated is a Gaussian kernel function. You can see it's not symmetric because I ran out of space. It should be symmetric, right? This one goes all the way to the infinity, the negative infinity, and this one goes to the positive infinity. So the idea, if we have, we're assuming data is kernel, Gaussian kernel is a very popular and often used kernel. There are other kernels. But for our DenClue methods, we use Gaussian. The idea is when we have a set of data here, and we're assuming that this data is generated by, so we're using one univariate example now. It's generated by one variable x. And what we can do is on every data point, we put a kernel function. So we will use that point as the mean and put a standard kernel function on top of it. So when we do that, you can see that every data point actually going to have, see, 1, 2, 3, 4, 5. We have 5 points. We put 5 kernel curves. So every data point here is actually accumulated. On top of it, there are 5 kernel functions curve on top of it. Even though you only see 1 for this one, it's not only because this one is further away from others. It seems like those all reached 0, but I deliberately showed here this is not 0. It's approaching 0, but it's never 0. So on top of every point, there are 5 dotted curves, and we can sum them up. If we sum those curves up, you will see that the area that with more dense points, the curve going to be accumulated taller. So this is the intuition behind the kernel density estimation. If for n points, now we have 5, we just add up the kernel functions, and then because we have 5 kernel functions, the area under the kernel would be 5, but we want it to be a probability distribution, therefore we'll have to normalize it. Divide it by 5 so that the area under the curve remains 1. So f hat x is actually a density function. So this is the idea. As you can see, we can immediately see how it can be used in clustering because we can look at the tallest points and believe this point air under it must have lots of more points than those curves that represent smoother or very low points. They will have scattered points. So do we have questions? Kernel density estimation? Okay, so apply this in DenClue. Here we want to introduce.
Sorry.
Yes.
Question.
So
just to confirm, the reason we have 5 of these kernel density functions is because we have 5 points. So
yes.
If you had 10,000 points or 1,000 points, you'd have 1,000 of these,
yes.
and you just repeat the same process of
correct.
Okay.
Yes.
So essentially here we kind of see 3 little peaks, so that means 3 clusters.
Right. Whether it's going to be a cluster, later we're going to talk about this. Not every little peak will be considered a cluster. You will have a threshold because those could also be noise, right? Only one point. You have one point very far away from others. It will still have a little bump. It is not really a cluster that you want. Later in maybe in 5 slides, we're going to talk about thresholding.
Thank you.
That this gave you a clue that that densely clustered area is going to have a curve that looks different from less dense areas. Okay, so that's the idea. To emphasize, to further this, when we look at the kernel function, we have x minus x sub I. So this shows us that we can use the Gaussian kernel to actually quite intuitively model the influence of a point on its neighbors. So this point have a stronger influence on this point. This point is closer to this point, so this bar is higher, taller. This point has less influence on this black point because it's far away. So this allows us, the kernel function allow us to model the influence, the points that will have more influence on the points that's closer to it. And here, we're not just using the kernel, the Gaussian kernel, we also use the smoothing parameter h. In the formula, what you can see, the location of h is here. This corresponds to the location of sigma, right, in Gaussian. So h actually tells you, can adjust this kernel that you want to use to see how smooth this curve going to be. The greater the h, the smoother the curve is. The smaller the h, the more pointing this curve is. So h is a parameter that you can adjust as a user. So here, when we so earlier we talked about this, and we have a question whether whether those tip of the hill will all be considered as a cluster, and in DenClue, a concept called density attractor is defined. So the attractor are basically some peaks. So we already observed that this after all those kernel curves being accumulated, we're going to see higher peaks and lower peaks, and some of the peak are going to end up to be density attractors. So here we're using x as one variable to illustrate the idea. It's very easy to see, and x certainly can be vectors when you have multivariate data, and the formula for multivariate data is just adding a vector sign on top of those x's. So intuitively, if we have a two-dimensional data set, we might end up with mountains and hills, valleys like this. other more examples that you can see, we use different age, resulting in different contour on top of the surface. And we can use a threshold, a cutting board, to cut this and get a projection to see where the clusters are. So the points close to a density attractor forms a cluster. If we go back to see the here, if we have decided those are density attractors, then all the points that's attracted to this points will be considered belonging to the cluster with this density attractor. I know that point has not been made very clear. We will clarify that shortly. As this graph shows, this cluster can be of different size, shape, and densities. I mean, depending on where you thresholding the thing. And this can also be used to generate a partitional cluster or hierarchical. Hierarchical should be clear to see, because when you adjust this, this hyperplane, you would create hierarchical clusterings. The partitional would occur when you're actually just looking at those density attractors separately. So each density attractor is going to form one cluster. Those clusters may be connected, but it does not have to. This says what we already said. Oh, one point to make: this kernel density function is different from the kernel tricks that we talked about when we did support vector machines. Kernel density function has this properties. The functions all has to be 0, so above the horizontal 0 line, and it's symmetric, and the area under the curve has to be 1. We're using Gaussian kernel, but there are other kernels. For example, square kernel. This square kernel has area under it to be 1, 2. I think we have covered all of those. So next thing we want to know is actually how do we find those density attractors? And this has to do with a threshold. So we know that we're going to have a curve with mountains and valleys. So the density attractors are those local maxima. So those are the tip of the mountains with density greater than a threshold. Okay. So if this is our function, the density function for any point. So let's see that density function going to look something like this. At any point, we want to find out on which mountain tops is my local density attractor. So again, this using the degree hill climbing method, that we find the gradients of this for this point, gradients pointing to the faster growth direction. So we move these points by a small amount, which is governed by the learning rate. And we move up hill climbing until we climb to a point. Going further will give us a smaller function value. And that's the one that we stop. That's our local maximum. That's our density attractor for this point. So for other points, they will do the same, finding their local maximum. The algorithm will not know where the global maximum is. They will all know that we reached a tip that's closest to me. And that's all the algorithm cares. So those are the tips. But not all of this is going to be considered density attractors because we have a threshold. Our threshold said that local maxima must have a density greater than a value. So this f has to be greater than this threshold. think we covered everything on this slide. So here is one example when we have a curve, looks like this. We have this many tips, and our density threshold is set here as the dotted line shows. And we can see here we have 1, 2, 3, 4, 5 local maximum, but we only have 1, 2, 3, 4 density attractors.
I have a question.
Yes.
That threshold that you talked about in the previous slide was to find the number of clusters or the center for clusters, right? Or something else?
Find the number of clusters. So these slides will find the local maximum for all the points.
Okay.
So this point is going to find its local maximum here. If we have a point here, it's going to find its local maximum here.
Yeah, this is applied after we find the local or global maximas. Then we can find, based on a threshold, then we can find the cluster corresponding to each sample, right?
We don't know where the local global maximum is. It doesn't matter.
So, okay, that threshold was for finding the center of the clusters, right?
No, the threshold is for finding which of the local maximum is actually viable. It represents a cluster.
Yeah.
Right.
And then after we find the clusters, we use the gradients to find the local maximas for each point, right? Is that right?
Okay, I get it. Hold on one moment. So at this point, what do we know, what we don't know yet, right? So here's what we know. We know our kernel function.
Okay, okay.
We know our observations.
Okay.
We know a threshold.
Okay.
Right? So this gives us a list of dots here, using again one-dimensional example, a list of dots here. Right? And we know the curve looks like this. We know there is a curve on top of those dots. Now our goal is to assign those data observations to different potential clusters.
Okay.
So our potential clusters are those peaks, right? So we actually using the function, see, we know x, we can find this x, right? The value. So therefore, we can find it where on which point on this curve it resides, right? So that dot, our observation is presented on this curve. And now there are two directions we can go, right? If you have actually more variables, you have a number of different directions to go. We're actually using the function. We compute the gradient. That gradient gave us the greatest increased function direction, right? So we go move up, move up, move up. So for this one single point, we have to move this projected point up to its tip to find, this point is attracted by this local maximum.
Okay. Okay.
So this point is potentially assigned to this cluster. This may not be ending to be a cluster if its density is too low.
Oh, so then now we use the threshold.
Yeah, that's the threshold now we're using.
Okay, makes sense.
Right. If we cut the threshold here, then every point here going to be noise or outliers. Only this one forms a cluster.
Okay.
Okay, good.
Question about H. You said it kind of does a smoothing effect, but what is the impact on actually the influence of finding our maxima? What is its broader impact if I increase H versus decrease H? Will I find more clusters?
Increase H and decrease H? Yes, it was certainly H parameter going to make this curve change the shape of this curve. So if you have, I think I have a few pictures, yes. But do we have more questions on this?
Yes, one follow-up question there. So just to clarify, what you're saying is on this is on slide 65, that the point is assigned to a cluster based on whether the curve at that point is going up or down. And so if it's going up, you say, okay, it's in this cluster versus not, or is that?
Not going up or down. It has to go up. It has to find its tip.
Okay, so the one that, because you could traverse the curve either to the left or to the right, but if you go to the left, your sort of the derivative, I guess, would be dropping.
Right, exactly.
So that's why you go to the right. So then if you're at the valley, you might be able to go either way. So I guess in that case, you could assign it to either cluster.
It will never happen to have exactly 0 here. It will go to one of the two directions.
Okay, I guess, yeah, probability of that, especially once you have many points, probability is very small.
Okay. It will be 0, 0, 0, 0, 0 something, but it will be something.
Okay. So unless, I guess, the H is really like flattens it so that, because as you said, then the H allows you to make really narrow ones or really wide ones.
Yes.
So if you make really wide ones, then I guess there's more overlap, but...
Right, so every point is going to have a stronger influence on the neighbors, even the neighbors that's not very close. So here you can imagine, as you can see, the influence here is very narrow. The points only influence its neighboring maybe 2 or 3 data points. So it will have, if you're using an H which is very small, you're going to have lots of outliers. That's not included. You're going to have clusters that's really dense. If your H is greater, then every point is going to exert some influence on other points. So any points that's further away from any cluster would still be on a reasonably high hill slope. So if you, depending on where you choose your threshold, your cluster going to be larger and looser. I mean, not very dense.
So depending on the application, or depending on how many clusters you want, is that how you decide H?
I think it depends on how, see, the resulting shape going to be very similar. After you examine your result, you see lots of outlier have been included in your clusters, then you want to make your H smaller. After you examine your clusters, you see some useful data points has been excluded, then you want to increase your H. So there are more, so this example basically showing, so earlier we showed the effect of the parameter H. This is exactly very similar to our lambda when we're doing radio kernel in SVM. Exactly the same idea. The effectiveness of the noise threshold, as you can see, if we increase the threshold, then very little points going to be included in the clusters. If we decrease our threshold, then our cluster going to be bigger, and we can have different shapes. And this also shows a hierarchical cluster is possible now, because all the points here is subsumed in those clusters, and additional, when you lower your density furthermore, those cluster points are combined into bigger clusters. Do we have questions? Okay, so feature of DenClue compared to other density methods, it's very fast. It's flexible for both center-defined clusters, which are the ones that's defined by the cluster attractors, or arbitrary shaped. Oh, did we talk about arbitrary shaped? Arbitrary shaped is going to happen if your center-defined clusters overlaps each other, touch with each other, or you have some connecting points that actually pass the threshold. That should be intuitive to see, but I just want to make it clear. So different shapes. Significantly faster, and it's very good for numerical data with large amount of uniformly distributed noise. You can see that. It needs several hyperparameters. So as you can see, we always list parameters as the calm part, the but part, because setting parameters is always a challenge. Here we need the H, the density threshold, and the learning rate. So those are all adjustable, and you know how to set them. It doesn't work well with high dimensional data. I mean, most of the clustering algorithm does not work very well with high dimensional data, because in high dimensional space, the distance is not that well defined. But for DenClue, because in high dimensional data are all looking like uniformly distributed. So it's hard to find those attractors. It will find good clusters, but it will miss lots of clusters.